Hello. This is the last lecture of the workshop um, about algebra. So, so today I want to show you the power of algebra, and it's uh, the introduction of algebra to the Western world about 1,000 years ago um, did change pretty much uh, the Western world on science, on mathematics, and because that caused many scientific discoveries and also um, technologies. And so today I just want to show you some examples about the power of algebra. So the subtitle today of this lecture is called "To the Infinity and Beyond." and and you'll see that how algebra can handle infinity. Okay, so uh, there is a story about a 5-year-old student. His name is Gauss, and who later became a great mathematician. So the story goes that one day his teacher wants to keep him occupied, and so his teacher gave this problem. Is so his teacher want him to add 1 plus 2 plus 3 plus 4 plus 5 and all the way up to 100. And so the teacher thought you might take a while. But to his surprise, the young Gauss came up with the solution pretty much immediately. And that's actually the right answer. So teacher was surprised and asked him, how can you do that so fast? Well, the thing is, he didn't actually adding it, even though he was told to add those together, but he didn't do it because the teacher just wanted to know the total sum. So he figured out a way of finding the sum without actually add all them up. So what he found is that there's a pattern. You can see that 1 plus 100 is 101. And then if you add to 99 here, then 2 plus 99 is still 101. Then 3 plus next one, 98, is also 101. So therefore, there are 50 pairs of those numbers, and the sum of the numbers is always 101. So therefore, the total then will be 50 times 101, and which give us 5,050, which is pretty fast. And so it shows that sometimes we don't have to just follow the process if we know what is objective. Because if the teacher said you have to follow that, that's a different story. But the teacher just want to have the total sum. And so young Gauss find a way to get there. And this actually turned out not only just working for 1 through 100. You could do the same thing for, say, 1 through, add that, and all the way down to 999 plus 1,000. And you can find the pretty much same pattern. It's 1, 0, 0, and 1. And 2 add that is 1, 0, 0, 1. So we got how many? 500 of those times 1, 0, 0, 1. So that gave us, that's going to be a big number here. So 5, 0, 0, 5, 0, 0. So we got, I hope I got this right. We got, okay, so that's what we have. And if we're going to add this, it'll take a long time. But this actually also true for adding to, like, say, 1 through 1 plus 2 always goes to, say, 10,000, or 1 through that goes to 1,000,000. We can do the same thing, but can we do something that we just do it once for all and came up with a formula that we just plug in the formula? And actually it turns out that's what algebra can help us to do. So let's clean this up. Okay, so in terms of algebra, what we're going to do is this. So let's see, we 1 plus 2 plus 3 and all the way to a number. We don't care what the number is, but we know it's a number. Okay, so to the n. So now we put, say, okay, let's see the sum is equal to that. But if you notice, one of the properties of this thing is that it doesn't matter what order we have. And so therefore, we can rearrange it, but that still gave me the same amount. We arrange it like that, and then there will be n minus 1, then there will be n minus 2. Then or we just go in the other way around. So 3 plus 2 plus 1. And now you can see, if we just add every pair, this gives us n plus 1. Then this gives us also n plus 1. And this gives us also n plus 1. And all the way down to the last is n plus 1. So then how many of those? We know we have n of those. So therefore, if we add them together, so basically add this together, then s plus s is 2s. Then we know we have n of the n groups n plus 1. So that'll be n times n plus 1. And therefore, we can divide all times half on both sides. Then our total then it becomes half n times n plus 1. So then we can just use that to apply to whatever things we are doing. For example, if we just do 1 through 100, now our n is 100. So if you plug that in, it's half 100 and 101, which is same as 50 times 101 give us 5,050. So that just shows the power of algebra, that we can come up with a formula. So that way, then we can cover any possible numbers that if we want to do, it doesn't matter to what numbers. We can just do. We can find the sum just by plugging this formula. And okay, so next something I want to show you is what happens if we have to add, and we have to add not just to a big number, it's just add to infinity. For example, what is 1 plus half plus 1/4 plus 1/8 plus 1/16, and so far, and just going forever to infinity. Okay, so how do we deal with that? And definitely we cannot add them. There's no way we can add them. And even just have most powerful computer cannot do that because it goes to infinity. But with algebra, we actually can show that the sum actually is a fixed number. It's a definite number. So even though we add infinite number of numbers, but the sum itself is finite. So we got s equal to that. And there's something we can see. If we multiply 2 on both sides, and what we see that, then we times 2 on all of that. So we see 2 plus 1 plus half plus 1/4, because the 2 has to distribute to all of that, and plus 1/8, then plus infinity. And then we can simply use this one to minus the top. So we have 2s on the left is 2s minus s. On the right is, we know all that is the same as all that. So we got 2. So therefore, 2s minus s. So therefore, the sum actually is 2. So even though there are infinite number of things, we don't have to add them. We're just using algebra to find the total. All right, and I'm going to show you another one. Is how do we find something is irrational number? And so what is an irrational number? The irrational number, oh, I want to go back. The irrational number is, there's definition for that. The irrational number is, I won't go here. The rational number, so first of all, what is rational number? Rational number is a number we can write as a fraction. So for example, 2 over 3, that's fraction, that's rational. This is a quotient of two integers. So the top is integer, bottom is integer. And also an integer like 4, we can write as 4 divided by 1. So it's still the quotient of two integers. And so therefore, any integer and plus all the fractions together, that's called rational numbers. It's a number family. And then what is irrational number? And how to actually become about, how do people find it? So the irrational number is basically not a rational number, which means you can not write the irrational number as a fraction or as a quotient of two integers. Now, for example, pi is a irrational number, very famous, and we know that it won't end. It's keep going forever, but this also means they don't have patterns. Not only it will say the decimal, if you write the decimal, 3.1415 keep forever, but there is also no patterns in those digits. But in the ancient time, people don't think this is irrational. And actually, if you look at Old Testament, and when God told Moses how to build a temple, and in there, pi actually is 3. And if you read the Bible, you'll see that it's just talking about the the diameter and the circumferences, and there pi is 3. And for many practical purposes, 3 is good enough. But later on, they find actually pi we can write as 22 over 7. That's another one. And then later on, you'll find the two other rational numbers and can be very close to pi. But it's only until pretty late. It's only until 1761, I hope I remember right, that was proven that pi is a irrational number. But there is, actually it turns out there are many, just infinite number of irrational numbers. And, but the first irrational number is square root of 2. And that actually, people not only find that this is irrational number more than 2,000 years ago, but someone actually proved it to be a irrational number. So the significance for number pi actually came from the Pythagorean theorem. Pythagorean theorem, if you remember, said if you have a right triangle, you got A, B, and C, then C squared is equal to A squared plus B squared. So this is called the Pythagorean theorem. And is a ancient Greek person called Pythagoras. And he actually have a society, it's a secret society called Pythagorean society. And there is a funny thing in this society is that they believe all the numbers in the universe are rational. All numbers are rational. And so just like basically, so we can a number either an integer or a fraction, but they are all rational. But his only theory actually shows that there is actually a number which is not rational. And so if you look at the Pythagorean theorem, so what happens if this is 1 and this is 1? So it's isosceles triangle, both lengths are 1, a 1 unit. Then on the hypotenuse, that gave us square root 2. And it turns out square root 2 is irrational. And for a while, the Pythagorean society tried to hide that fact because one of actually member of the society discovered this. And that member actually later was, according to legend, that member was basically killed because he didn't keep it as a secret. Okay, so now let's look. How can we prove that? How can we prove this? Square root 2 is a irrational number. Because one thing we just cannot, by trial and error, we cannot just put any, say, this is maybe 4 out of 3, or maybe 5 out of 4. We can try all the numbers, and but there's an infinite number of those fractions, so we couldn't even prove this one is a irrational number. So what are we going to deal with that? So here is what algebra can do. And there is a very important technique to prove something is true, is that by assuming something is true. So if we, well, technique is to prove that something is not true. It's by assuming that is true. And then we follow the logic and we come down to a contradiction. And if that's the case, then we know that things we're trying to prove is definitely not true, it's false. Okay, so that's the technique we're going to use. And so therefore, we first assume square root of 2 is rational. That means we can write as P over Q. And also further, we assume that P and Q, this is a simplified fraction, which means P and Q only have one common factor of 1. So 1 is only common factor between P and Q, and that's what we call what we mean by simplified fraction. Like for example, 4 over 6. So the common factor between 4 and 6 is 2 and 1. So therefore, it's not done yet, not simplified. So if we divide by 2 on both sides, so 2. Then we got 2 over 3. Now 2 and 3, only common factor is 1. So that's the simplified version. So here we're assuming that this is simplified, which means P and Q has only one common factor of 1. So if that's the case, and one thing we know that if this is true, so that's our assumption, but something has to follow. Then we know square root of square is equal to P and Q squared. So basically, if we have equation, then we can square on both sides. And this has to be true. And then on this side is give us 2. Then on this side, we got P squared over Q squared. And from that, we know P squared is equal to 2Q squared. Now this is something interesting because we have a factor of 2. which means q squared is an integer. Remember, p and q are all integers, so the square is also integer. That means p squared is an even number, which means they have a factor of 2. But if p squared is an even number, then p has to be an even number too. So now we know p has to be an even number. Now, if p is an even number, then we can write p as 2 times another integer. Let's just say it's n, another integer. Doesn't matter what number is, but we know this is a even number. So now we can plug it back into this equation, because we know that follow the assumption, we know this is true, we know this is true, and then we know this has to be true. So that's basically when we do algebra, it's basically this if-then statement. If this is true, then this must be true, then that must be true. And that's what we call it is a logical process. Okay, so now we know P is 2n. We can write P at 2n as an even number. So now we have, based on this equation, we got 2n squared equals 2q squared. And on this side is actually 4n squared. And now we have 2q squared. Now then we divide by, times half on both sides. Then this side, it got 2n squared. And then on this side, the q squared. Now we have this q squared is also have a factor of 2. That means q squared is an even number. Then we have a problem. That means q is also an even number. So now we have not only p is an even number, then q is also an even number, which means p and q not only have a common factor of 1, they also have a common factor of 2, because both are even numbers. Both have a factor of 2. So that's a contradiction, because when we started our assumption, p and q only have one common factor of 1. But now we find not only have 1 as a common factor, also 2 is also a common factor. So this one, so that we come to a contradictory conclusion. So the only way to solve that contradiction is to show that square root of 2, well, it has to be an irrational number. So that's the only way that we can solve this contradiction, is that square root of 2 is not a rational number. Therefore, square root of 2 has to be a irrational number. So that's kind of one of a very good example of algebra. And during the whole process, except 2, we didn't use any other number. Yet we proved the square root of 2 is an irrational number. All right. So there is one more example I want to give to you. It's also to do with this Pythagorean theorem. It's called Pythagorean triples. And if you remember, we know Pythagorean, we have those triples, this 3, 4, 5. And this actually is known, this triple 3, 4, 5 is known for at least more than 3,000 years ago. And in many Asian cultures have the record of that, like the Chinese culture, the Babylonians, the Persians, and they all have something called the triplet, 3, 4, 5. It's just like in the West, we know the triple from Pythagoras. And most likely, he actually didn't discover this theorem. Most likely, he just recorded it. He talked about it. So that's a triples, which means 3 squared plus 4 squared is equal to 5 squared. Okay, very, very famous theorem. But there are many of those triples, not just this one. We actually have 6, 8, and 10, and we also have could have 9 and 12 and 15. So how do we know? How do we come up with those triples? Actually, it's pretty easy. If you think, let's see, we know this is true. So therefore, what happens to 3 times an integer plus 4 times an integer? What are we going to have? And we know this is 3 squared, and this is a squared, and also 4a here is 4 squared and a squared. And that, we know a squared is a common factor. We can write as 3 squared plus 4 squared times a squared. And then, based on what we know here, that's 5 squared and a squared. So which is 5 and a squared. So we know 3a squared plus 4a squared is equal to 5a squared, and a can be any integer. So therefore we can generate, if a is equal to 2, then we can generate 6, 8, 10. If a is 3, we generate 3, 12, because 3 times 4 is 12, 3 times 5 is 15, that. And then we just keep going. So if a is 4, then we have 12, 16, and 20. So we can generate that. And all because we can use algebra to prove if this is true, and we know this is true, we can verify it, then this has to be true. Then that means we can generate infinite number of Pythagorean triples. All right, so I hope I somehow was able to show you the beauty and power of algebra. And well, thank you for come to this workshop. I hope that you feel more confident about algebra and about actually learning algebra on your own. All right, I'll see you. Bye.